record. Now we're recording, so let me just repeat. This is lecture 9 on the calculus of vector valued functions, and I just reviewed a little bit about the derivative of a vector valued function. You have a function r of t, which traces the trajectory of a particle moving in space, and its derivative is defined by the usual difference quotient from Calc 1. And we have this notion of a tangent vector, and if you take a tangent vector and divide by its length, you get what is called the unit tangent vector. So let me go share the screen with the text, and then it's much easier to see. So here is the same picture I tried to draw by hand, but of course it's much clearer here. So r of t is this particle moving in space like this, and here's this position p at time t. At a small time delta t later, here's the position at t plus delta t. And if you take the vector from p to q, that's this difference. It's the vector from the position at t to the position at time delta t. If you multiply by the scalar 1 over delta t, you've normalized this tangent vector a little bit. And if you look at the sequence of these vectors, as delta t goes to 0, those vectors might approach a limiting vector. And if they do, that is what is called the derivative vector. So, and in terms of coordinates, you can work out the formula, and it's very simple. You obtain the derivative. Let me just go back. You obtain the derivative of a vector by differentiating each coordinate. And so if r of t, this vector valued function, is given by f of ti, g of tj, h of tk, you differentiate h, f, g, and h, and those are the coordinates of the tangent vector. And it's pointing in the direction of motion. Sometimes, if you really are interested in the direction, the magnitude or the length of the tangent vector doesn't matter. So you can divide by the length, and you get what is called the unit tangent vector, which is a direct vector of length 1 pointing in the direction of motion. So that's pretty simple, really. It's just a definition you have to remember. So a simple example is you have this vector value function, t squared 4t and 4 log t. And if you wanted the derivative, you differentiate each of the coordinates. You'll get 2t4 and 4 over t. And here they are, 2t, 4, and 4 over t. The length of this vector, if you calculate it, is this. So the tangent vector divided by its length gives us this unit tangent vector. And just the way in Calculus 1, you spent a lot of time learning rules for differentiation, sum rule, product rule, quotient rule, and chain rule, there's similar rules for derivatives of vector valued functions. The derivative of a constant is 0. The derivative of the sum of two functions is the sum of the derivatives. Here's a product rule where you multiply a vector by a scalar function f of t, and you get exactly this product rule. And you have a chain rule, which is exactly this. These formulas are completely analogous to what you know for ordinary functions, real valued functions of a variable. And what is very nice is the product rule works in exactly the way you would expect for the dot product of two vector functions and the cross product of two vector functions. So the derivative of the dot product is the dot product of the derivative of u with v plus the dot product of u with the derivative of v. And the analogous formula is true for the vector product of two functions. And this really summarizes everything there is to know about these functions and their derivatives. But of course, calculus involves two operations, differentiation and integration. And the way you integrate a vector valued function is simply to integrate each component one by one. So you can define the indefinite integral as an antiderivative. So if little r of t is a vector valued function, if you have a function capital R of t, which when you differentiate it gives you little r of t, that is the indefinite integral. And you integrate a vector valued function by integrating its x, y, and z coordinates separately. So this definition summarizes everything very neatly. And just as an example, here we have a vector value function t over root t squared plus 2, e to the minus 3t sine 4t plus 1. These are the coordinate functions. If we want to integrate this vector valued function, you integrate the coordinate functions separately. Now, that only makes sense if you know how to do the integrals. But you're expected to know Math 175 and 176 in order to take Math 226. So you have to be able to do these integrals. So the integral of t over the square root is square root of t squared plus 2. Square root of e to the minus 3t is minus a third e to the minus 3t. The integral of the sine is minus the cosine and so forth. So you compute the integrals of the x, y, and z components, and that gives you the integral of the vector valued function. So I don't know if I'm going over this too slowly or too quickly, but you have to be studying this at home, and then things should become clear. So let me do one or two problems, and so if anyone has a problem they would like me to do, tell me right now, and I'll do it. Otherwise, I'll just pick some problems at random. Well, let's see. I'll do number 29. So if you look at 29, r of t is the vector valued function cosine of 2t for 3 sine of 2t. And we're asked to find the unit tangent vector at t equal to pi over 2 radians. So let me go to my paper. And here I wrote down the problem. R of t is cosine 2t for 3 sine 2t. So the tangent vector is what we get by differentiating each coordinate function term by term. The derivative of cosine 2t is minus 2 sine 2t. The derivative of 4 is 0. And the derivative of 3 sine 2t is 2 times 3, which is 6 cosine 2t. So the unit tangent vector if we evaluate this at pi over 2 is minus 2 times the sine of pi, 2t, 0, 6 times the cosine of pi. Sine of pi is 0. 0 is 0. Cosine pi is 1. This is minus 6. So the derivative at pi over 2 is the vector 0, 0, minus 6. The length of this vector is 6. So the unit tangent vector at pi over 2 is 1/6, 0, 0, minus 6. So that's 0, 0, minus 1. So that's the unit tangent vector. Okay. Any questions about that? All right, well, let's look at another problem. Suppose I take number 39, I'll do 39 and 40. Well, I'll start with this set. So I want to make it a little bit harder. So this is going to be 43 to 48. So for those problems, we have the vector function u of t, which is 1t squared, and the vector function v of t, which is 2 squared minus 2t1. And we want to compute, this is number, find the derivatives. So we want to find the derivative, number 43, of v of e to the t. So this is a composite function. And remember, the rule is if you have v of a function f of t, the derivative with respect to t is the vector function differentiated f v prime at f of t times the scalar f prime of t. So in this case, v of t is here's v of t, and f of t is e to the t. So the derivative with respect to t of v of e to the t is what? So this is my function v. So v prime of t, we differentiate term by term, we get 2t minus 2, 0. So if we evaluate this at e to the t, this is v prime of e to the t times the derivative of e to the t, which is e to the t. I'd rather put the scale in front. This is e to the t times the vector 2e to the t minus 2, 0. So that's 2e to the 2t minus 2e to the t, 0. And that's the answer. Right. So let me just make sure this is clear. V of t is the vector valued function t squared minus 2t1. So v prime of t, you differentiate term by term, you get 2t minus 2, 0. And when you evaluate this at the number e to the t, this is 2e to the t minus 2, 0. And then we're multiplying this by e to the t, and we'll get 2e to the 2t minus 2e to the t and 0. Let's do problem number 48. So again, u of t is the vector valued function 1t squared. V of t is the vector valued function t squared minus 2t 1. What is the derivative of the dot product? So let me do this in two different ways. First, I can use the formula that the derivative of the dot product of two functions is the derivative of the first dot product with the second plus the first dot product with the derivative of the second. So what is the dot product of u of t? You differentiate each coordinate. Derivative of 1 is 0. Derivative of t is 1. Derivative of t squared is 2t. Dot product with v of t, t squared minus 2t1. Plus u of t, 1t t squared. Dot product with the derivative of v, which is 2t minus 2, 0. This dot product is 0 minus 2t plus 2t. And this dot product is 2t minus 2t plus 0. We get 0 plus 0, we get 0. So the dot product, by the product rule for the dot product, is the constant function 0. Let's check. One way to check is to compute the dot product first and then differentiate. So the dot product of these two functions is 1 times t squared plus t times minus 2t minus 2t squared plus t squared, that's 0. So the dot product is just 0, so the derivative is certainly 0, and that checks. Let's look at number 47. We want to differentiate the vector product, u cross t. So the formula says this is u prime cross v plus u cross v prime of t. So I have to compute these two cross products. So to compute u prime of t cross v of t, I have I, j, k. U prime, so remember u was 1t and t squared, so the derivative is, so u is 1t and t squared. Sorry, I'm putting in u prime. U prime is 0, 1, 2t, and v is t squared minus 2t1. Plus the cross product of u and v prime. U again is 1t t squared. V, when we differentiate it, is 2t minus 2, 0. You see, so what is this? This is, when I compute this cross product, it's 1 plus 4t squared I minus this times this, or this minus this, minus is plus 2t cubed j, and this minus t squared k. And this this cross product is 0 minus 2, so that's 2t squared I. The j component is 1 minus, so it's minus times minus 2t cubed is plus 2t cubed j. And the k component is minus 2 minus 2t squared. Well, that's minus 2t plus 2t squared. Okay. And when I add that up, I get, looks like 1 plus 6t squared I plus 4t cubed j. And I have minus 2t and minus 3t squared. So in the unlikely event I did this correctly, this is the cross product. But this check, right? Simplest way to check. See here, what I did was I didn't compute the cross product. I used the product formula. Then we compute the cross product and then differentiate. So u of t cross v of t. So this is I, j, k. U is the vector value function 1t t squared. V is the vector value function t squared minus 2t 1. So this is equal to t plus 2t cubed I minus 1 minus 2t squared j plus minus 2t minus t cubed. So that's minus 2t plus t cubed k. So then if I differentiate u of t times v of t, I get 1 plus 6t squared I. This is 4t j. That's the problem. I'll come back to that. And I differentiate this, I get minus t plus 3t squared k. So these don't agree, so I better find out where I made a mistake. So let's start with this. The function u is 1t and t squared, and v is t squared minus 2t1. So when I take the vector product, I get t plus 2t cubed for the I coordinate. For the j coordinate, it's minus 1 minus t to the fourth. Oops. 1 minus t to the fourth. So when I differentiate this, I get 4t cubed. And the k component is minus 2t minus t cubed, or minus 2t plus t cubed. And when I differentiate that, I get 2 plus 3t squared. And here, what did I get wrong? Let's just double check this k component. So this should have been a 0. No, it's not right. Sorry. That's correct. T squared minus 2t1. When I differentiate, I get 2t minus 2, 0. So the k component here is plus, it's plus t squared. No, it's this minus t squared, that's right. And the k component here is -2 minus 2t squared. This should be -2. And then this gives me -2 and minus 3t squared. Oh, and that's what I got. So I had mistakes everywhere, but I figured them out, and now everything is good. Any questions about this? So let's go back to looking at the book. So there's an important physical interpretation for the first and second derivatives of a vector valued function. So if you have the position of the particle given by a vector valued function r of t, the derivative is called the velocity. So if you have a vector valued function or a curve tracing out the trajectory of a particle in space, at every point at every point on the curve, there's a derivative vector, and that is what is in physics the velocity. So velocity is just another name for the first derivative of the position. Speed is something different. Speed is not a vector. Speed is a scalar, it's a number. So the speed of a vector at a point is the length of its velocity vector. And it's important, even though in common discourse, it's usual to confuse or interchange these words or treat them as synonyms, velocity and speed. Velocity is a vector, speed is a number, a scalar. The speed of a particle at a point is the absolute value, the magnitude of its velocity vector. And if you differentiate the velocity, so that's like taking the second derivative of the position, you get a vector that is called the acceleration. And those are the three basic expressions in elementary mechanics and beginning physics: position, velocity, and acceleration. And speed, those are vectors, and speed is just the absolute value of the magnitude of the length of the velocity vector. So if you're given a vector valued function and told to find the position, the velocity, and the acceleration, the position is the function, the velocity is the first derivative of the position, and the acceleration is the first derivative of the velocity, which is the same as the second derivative of the acceleration. And hopefully you all took Math 155 and 156, so you learned some computer algebra graphing program. Maple is the best. Some people use something different. But it's very hard to draw curves in three-dimensional space by hand. But there's a command in Maple called plot 3D, three-dimensional plotting, that gives you beautiful, beautiful pictures. So I don't want to move ahead too quickly, and so I'm just going to say a little bit about what's in section 14.3, and I'll talk about it more next week. Remember, we have a funny calendar at CUNY at the beginning of every fall semester. So next week there's class on Monday, but not on Wednesday. And the week after that, there is no class on Monday, but there is class on Wednesday. So we have one class next week and one class the following week, and then we're back to the normal schedule for the rest of the semester. So if you have a function R of t, a vector value function, and each coordinate function is a linear expression in the time variable t. So x naught plus at, that's a straight line. These are straight lines, and if you put three linear coordinate functions together, you get straight line motion in space. This position vector is just tracking, moving along a straight line. It's the straight line that passes through the point x naught, y naught, z naught, and goes in the direction or parallel to the vector ABC. So that is what is called uniform motion. On the other hand, if you are in, for example, in the plane, and you have R of t, your position is a cosine t, a sine t. The a is the same in both the coordinates. This is circular motion, just going around a circle. And the velocity is this vector, and the acceleration is this vector. And the book observes that the acceleration vector is exactly the same as the position vector, but with a minus sign. So this means that when you have circular motion in the plane, the position and the acceleration are exactly opposite to each other. So position R, acceleration A are parallel but in opposite directions. And the dot product with the velocity in both the position and the acceleration is 0. So this is when something is moving in circular motion, its velocity is always perpendicular to the direction of motion. So let me just describe one or two of the examples that are done in the text, and I'll do it on a piece of paper because it's easier to sort of follow the details. So let's see what the problem is. This is about computing a path on a sphere. So we have R of t. So I'm looking at example 3 on page 886. R of t has x coordinate 3 cosine t, 5 sine t, 4 cosine t. And we want to follow this as t goes from 0 to 2 pi. And it's asserted that this is a trajectory on the surface of a sphere. So let's stop the share and take a look at the problem. So this is the problem we're given. R of t traces out this trajectory. This is its path in three-dimensional space as t goes from 0 to 2 pi. Why is this on a sphere? So what is the distance? What is the length of this vector R of t? So the length squared is the sum of the squares of the coordinates. So that's 3 cosine t squared plus 5 sine t squared plus 4 cosine t squared. That's 9 cosine squared t, 25 sine squared t, 16 cosine squared t. If we add these two terms, we get 25 cosine squared t plus 25 sine squared t. If I factor out 25, I got 25 cosine squared t plus sine squared t. But cosine squared plus sine squared is 1. So this is just 25. So the square of r of t is 25. So the length of the vector r of t is the square root of 25, or 5, for all t. So whatever this particle is doing, as it moves in space, it's always on the surface of this sphere of radius 5. So the path of this particle is some trajectory on the sphere. I have no idea what it is because I certainly can't draw it. But that is, this calculation shows us that the particle is always moving on a sphere of radius 5. What is its velocity? The velocity is the derivative of the position. So the derivative of 3 cosine t is minus 3 sine t. The derivative of 5 sine t is 5 cosine t. The derivative of 4 cosine t is minus 4 sine t. So at every instant of time, this is the velocity vector. What is the acceleration? It's the derivative of the velocity, which means it's the second derivative of the position. If I differentiate the velocity, I get minus 3 cosine t minus 5 sine t minus 4 cosine t. If I compare that to r of t, I see this is exactly minus r of t. So the acceleration and the position of this particle moving on the sphere, they're always pointing in exactly opposite directions, parallel but opposite directions. And you can also check that the position dot product with the acceleration, dot product with the velocity, and the velocity dot product with the acceleration, they're 0. So you can think of it somehow like this. As you're moving along, if this is the position vector, this is the acceleration vector, and these are the velocity vector. The velocity vector is perpendicular to position and acceleration. So we can now do some problems which are very similar to problems that you already did in beginning calculus. Let me look at let's look at an example. Let me go back to the text. So range, time of flight, maximum height. So suppose the motion of some particle starts at the origin. So you are shooting some projectile into space and it follows some trajectory. And if it's moving under the influence of gravity, if the only force acting on the particle, this satellite, this vehicle we're throwing up into space, the only force acting on it is gravity, that's a force which is always pointing downwards. It has no left, right, horizontal component. Its only component is in the negative z direction. And so here is the picture that we're given. We launch a particle in space. Its starting point is the origin, and its initial thrust forward makes an angle alpha with a positive x-axis. So alpha is some angle between 0 and pi/2 radians. And let's say the initial speed, the absolute value or the magnitude of the velocity is absolute value of v naught. Let's see. Let me just go back a bit. Actually, I'm hesitant to move too fast because if I follow the syllabus, which I try to do, the lesson for today was the previous section on the calculus of vector valued functions, the derivative and the integral. And what I really plan to talk about on Monday is this section 3, which is where so section 14.3, motion in space, is on the syllabus for discussion on Monday. And I think I'm going to wait until then to do it. I'm happy to answer any questions you might have about sections 1 and 2 in chapter 14. If you are working on problems and have questions, there's a problem session tomorrow morning at 11 o'clock, and I'm available then. Also, as always, if you have some problems and you can't make it to a regularly scheduled problem session, just send me an email and we can work out a time when we can both be available on Zoom. But if there are no questions, then I think I'm going to stop right here for today. Okay. So let me stop the share. And
Thank you, Professor. Have a great day.
you too. So
Thank you.
yes. Again, 11 o'clock tomorrow, I'm on Zoom if you have a question, and otherwise our next class is Monday at 11 o'clock. All right, be well, everyone. Have a nice weekend.